So, so depending on how we arrange our strain gauges, we can affect the output of the strain gauge. So basically, how sensitive our strain gauge is to different types of applied loading. So in this case, we have a beam, a cantilever beam, that's undergoing a applied normal force and a bending moment, and we put two strain gauges on the top surface and on the bottom surface of the beam. All right, and within our strain gauge, within our Wheatstone bridge, all right, we have two strain gauges and then two resistors. Right. All right. So the first strain gauge, all right, I'll put this as gauge 1. All right, we have gauge 4, and then we have two resistors R2 and R3. All right. The output across our gauge, or the output across our Wheatstone bridge is shown on the right, and then we have our input voltage on the bottom. Okay. So um, if we have strain on the top and bottom surface of our beam, that strain is going to be due to our applied normal load and our applied motion. So our applied normal load would be give us an axial stress, so it give us an axial stress, and that would be experienced equally on the top and bottom of the surface of the beam, and that would be equal to the force over the cross-sectional area, BH. All right. Now the bending stress, all right, would be different on the top and bottom surface of the beam. So that would be equal to minus my over I. Okay. Now, if y is positive, now y is measured from the neutral axis. Okay. So our the top surface of our beam, due to the bending moment, is going to be compressed. All right, while the bottom surface of the beam is going to be stretched out. So the top surface will be in compression, while the bottom surface will be in tension. All right. So with that in mind, um, what we can do here is we know that the strain in the top of the beam is going to be equal and opposite to the strain in the bottom of the beam due to that bending moment. Okay. So what we can do here, all right, is we know that this is our stress equation for both the bottom and the top of the beam. We can say for this case configuration that we've drawn on the top right, that our equation for our output voltage due to the applied strain would be equal to this equation here, and since 2 and 3 are just resistors, these would be 0. All right. Now, if we substitute in our strain due to axial loading and our strain due to bending loading, what we end up getting is that since the bending on the top of the beam is going to cause a compressive strain, while the strain on the bottom of the beam is going to cause an equal and opposite positive strain, or a tensile strain, these two are going to cancel each other out. All right. And we're left with just the strain due to the two axial loads. All right, now the axial loads on the top, the strain and the axial load on the top and the bottom will be the same. So because of that, we can simplify them just to be equal to the axial load, the axial strain here. Okay. Now, all right. Now, if we wanted to determine what kappa would be, all right, we would then divide our gauge factor, our equation for our output voltage for multiple gauges by the equation we developed for a single gauge, for a Wheatstone bridge with a single gauge. All right. So in this case, we would get 2. All right. So by using this method, we've made our our strain by using these two gauges. The major thing that we developed is that the strain gauges are now 2 times as sensitive than a single gauge in tension, and we're eliminating any contributions due to any bending moments or transverse forces acting on those two gauges. Okay, so we're going to talk about in the next video how we can use a similar idea to compensate for changes in temperature that we might see during the course of an experiment.